Note that if I replace each of the 0.05s that I have here by 0.05 divided by 2, then I've said that probability of A or B is less than or equal to 0.05, right? If I had said that we're going to use as our p-value cutoff for the first test 0.025, and I had said that we're going to use as our p-value cutoff for the second test 0.025, then if I had gone through this entire calculation, I would have ended up with 2 times 0.025, which is equal to 0.05. The Bonferroni method is just to use as our cutoff for each individual test's p-value the overall desired family-wise p-value divided by the number of tests. If I have 2 tests, then in order to have the overall probability of making at least one mistake be no bigger than 0.05, I'm going to compare each of the 2 p-values to 0.05 divided by 2. If I have 10 tests and I want the overall probability of making at least one mistake to be no bigger than 0.05, then I'm going to use as the cutoff for each individual p-value 0.05 divided by 10. That's the Bonferroni method, and this is why it works. What you can see here is that as the number of tests increases, this is very quickly going to become ungainly, right? If I have 100 tests, then all of a sudden the cutoff for each p-value is 0.05 divided by 100. So there are limits to the usefulness of Bonferroni. On the other hand, the simplicity of this method is fantastic, right? If you're writing a paper and you want to use the Bonferroni method, you don't actually have to go through and list all the p-values that you would obtain if you do the multiple comparison corrections, such as Bonferroni versus if you don't. Rather, you can just say, here are my p-values. If you want to think about a multiple comparison correction, note that I did 4 tests, so you should use 0.05 divided by 4 as a cutoff. And you can just say that and be done with it. Another thing that's fantastic here is we didn't have to say anything or make any assumptions about how these tests are related to each other. We didn't have to calculate the correlation between them. We didn't have to assume any particular format for our study, that we're looking at all pairs of comparing different groups, which is what a lot of the other tests assume. We didn't even assume that these are tests in the same context or done by the same researcher. None of that matters. All we're doing is dividing each cutoff by the number of tests so that we can say the probability of at least one mistake is no bigger than whatever the desired number is. And by the way, if instead of 0.05 our goal was for the family-wise coverage to be 0.1, awesome, divide 0.1 by the number of tests and that works fine. Because Bonferroni doesn't make any assumptions about how the tests are related to each other, in tests where we have certain particular kinds of relationships, Bonferroni tends to be conservative. Say 6 groups, and we're interested in doing t-tests to look at each pair of those groups. There are methods specifically designed to deal with that situation in the most efficient possible way. So if we use Bonferroni for that particular setup, we're going to end up rejecting less often than we actually could if we used a method that was set up to detect effects in that particular situation. So Bonferroni always works, which is fantastic, but if you have a situation where your data is formatted in a particular way, where there is some test particularly designed for that situation, that other test is probably better. Bonferroni tends to be conservative, but it is nice and simple, which is a fantastic feature.